Good morning, guys. So today we will see the further derivation part of this. As we have derived this equation in our previous lecture, okay, by using the governing differential equation for vibration analysis. Okay, so this is the first we have governing differential equation for a vibration object rod. Okay, so from this governing differential equation we have put this governing differential equation into our residual format. Okay, so if we will get first we will get the residual, then we will get the we will apply this residual to our weighted residual method, and we will solve this integral part. Okay, we have solved actually this integral part in our previous lecture, and we have got this equation. Okay, so this equation is nothing but rho into A into L by 6 into this matrix into U1 double dot U2 double dot, where U1 dot U2 double dot, this is the second derivative, rho square U phi dou P square. Okay, and this is your EA by L into this matrix will be U1 U is equal to EA dou U by dou X, EA dou U by dou X. Okay, so this is first one is your mass matrix, second one is your stiffness matrix, and third one is your load vector, or you can say a force vector, or you can say a boundary condition. Okay, so now which can be written as m times u double dot plus k times u is equal to f. So here this includes a time derivative and this includes a simple displacement. Okay, so first we will see the consistent mass matrix and lumped mass matrix, then how to solve this equation. Okay, so how to solve this equations, because for first element we will get first two equations, for second element if there are three nodes then we will get three equations, if the nodes are going increasing then we will get the number of equations on increasing manner. Okay, so we will get various equations, that is if n number of nodes are there, okay, then we will get n number of equations in this format. Then how to solve these equations, because this will include the second derivative of this displacement with respect to time, and here it's only included the displacement vector. But we have solved if the displacement vector is there, if the algebraic form is there, then we have solved our equations by using our Gauss elimination or by applying the boundary conditions, and we have solved such system of algebraic equations in previous chapters. But here it is difficulty that there is a second derivative term. U1 double dot, it is nothing but dou square U by dou T square. So this equation includes a second derivative term. So how to solve such type of systems? Okay, we will see this in this lecture also. Okay, so first we will see what is the basic difference between consistent mass matrix and lumped mass matrix. Okay, so we will see. So there are two systems, that is consistent mass matrix system and lumped mass matrix system. So what is the basic difference between these two? Okay, so we will see. So as we know that the mass matrix is given by mass matrix is equal to E into A into L divided by 6 in bracket 2 1 1 2. Okay, so this is the mass matrix we have derived in our previous lecture. So what do we mean by consistent mass matrix, and what is the meaning of your lumped mass matrix? Okay, so what do we mean by consistent mass matrix and what do we mean by lumped mass matrix? So as we know that these are the elements of this mass matrix, A11 for example, this is A12, this is A21, this is A22. So if we add these four elements, okay, if we add these four elements of this mass matrix, then we will get, so 2 times E into A into L divided by 6 plus E into A into L divided by 6 plus 2 times E into A into L divided by 6 plus E into A into L divided by 6. Okay, so if we add these four elements of this mass matrix, then we will get 2 plus 1 plus 2 plus 1 divided by 6 times EA. So it it is nothing but 2 plus 1 3, 3 plus 2 5, 5 plus 1 6, 6 by 6 is equal to 1. So we will get only FEA-L, and it is nothing but the mass, total mass. It is nothing but the total mass of that element. Okay, so from this we conclude that this total mass is distributed over this element. Okay, so this total mass EAL is distributed over this element. Okay, it is distributed over this element. So we can say that such type of system it is known as the consistent mass matrix system. Okay, because the mass is distributed in equal manner over the element. So that's why such system is called as consistent mass matrix system. And second one is your lumped mass matrix system. If the mass is distributed over the end nodes only. Okay, if the mass is distributed over the end nodes only, then such type of system is known as lumped mass matrix system. Okay, so if the mass is, this total mass is distributed over the nodes only, so it means what? It is distributed like that, rho into A into L divided by 2 and rho into A into L divided by this. If such type of condition is occurring, then this is called as lumped mass matrix system. Okay, so in lumped mass matrix system, the total mass is distributed over two nodes only. Okay, or over nodes only. So we can write the mass matrix in this case like rho into A into L divided by 2 in bracket 1 0 0 1. Okay, so this is the mass matrix for lumped mass matrix system. And for this case, rho into A into L divided by 6 in bracket 2 1 1 2. This is nothing but your mass matrix for consistent mass matrix system. Okay, if the total mass is distributed over the element, then we can say that such type of mass matrix system is known as consistent mass matrix system. And if the total mass is distributed over only nodes, then we can write this mass matrix as rho into A into L by 2 into this matrix, and it is known as lumped mass matrix system. Okay, so in this way we can distinguish the consistent mass matrix and lumped mass matrix system. Okay, now we will see. Okay, this is about your consistent and mass matrix system, lumped mass matrix system, because such type of in your exam for 16 marks problem, they will ask to find out the natural frequency by using consistent mass matrix as well as by using lumped mass matrix system. Because by using consistent mass matrix, this will be for 8 marks, and by using lumped mass matrix, this will be for your 8 marks. Okay, so both systems will be asked in exam. So try to remember this mass matrix. For this consistent mass matrix, it is given as rho into A into L by 6 into this matrix, and for lumped mass matrix, it is given by rho into A into L by 2 into 1 0 0. Okay, so in this way we have distinguished this consistent and lumped mass matrix systems. Now we can write, suppose if this is the element, and if we have converted this body in 3 elements, like so 1 2 3 and okay. Now we know that for one element we have the equation that this mass matrix into, for first element it will become u1 double dot u2 double dot plus this k matrix, this will become u1 u2, and the boundary condition is minus EA dou u by dou x and EA dou u by dou x. Okay, then for second element we can write same, and matrix into u2 double dot u3 double dot plus k matrix into u2 u3 is equal to again minus EA dou u by dou x. This is for first node, this is for second node. Now this is for second node, now this is for dou u by dou x for third node, this boundary condition. Then again for third case, and it can be written as u3 double dot u4 double dot plus K matrix into u3 u4 is equal to this EA dou u by dou x, sorry, minus EA dou u by dou x for third node and EA dou u by dou x for your fourth node. Okay, so in this way you can write these three equations, first, second and third. So if we combine these three equations, we will get, okay, if we combine this equation, we will get this global M matrix. Okay, so suppose this is a global G, global M matrix times u1 double dot, u2 double dot, u3 double dot and u4 double dot plus global stiffness matrix into u1, u2, u3 and u4 is equal to, okay, is equal to what? So here I am writing this term right hand side here. So is equal to, in bracket, if we add these three elemental, if we add these three vectors, we will get first minus EA dou u by dou x at node 1, then this term at node 2 plus this term at node 2. So this is plus, this is minus. So this will get equal to 0. Then similarly, this plus this, 3 plus 3, because we need to add this 3 plus 3. So this will become also 0. And finally, last remaining term is EA dou u by dou x at 1. So EA dou u by dou x at node 4. So this will become like that. So what is the conclusion from this? So the boundary conditions, as we know that our general equation is M u double dot plus K u is equal to this load vector dou u by dou x minus EA dou u by dou x and EA dou u by dou x. So from this equation we conclude that the boundary condition is applied only at extreme nodes. That is, if this is the problem, the boundary condition is applied only at extreme nodes. So extreme node, this is the first node and this is the last node. So boundary condition is applicable only at extreme nodes, that is at node 1 and at node 4, and the remaining nodes, boundary condition for remaining nodes will become equal to 0. Okay, so this is the conclusion. So if we add these three equations and if we write down the global force vector, then we will get the boundary condition only at extreme nodes. It means, so it is applied, the boundary condition is applicable only at extreme nodes, that is at left node and extreme right node. Okay, and the remaining nodes, the nodes in between these extreme nodes will be equal to 0. Okay, so this is about your boundary condition. Okay, now which type of boundary conditions are there? So there are generally three types of boundary conditions which can be applied in general your vibration problems. So what are these? So first one is your free boundary condition. So boundary conditions, there are three types of boundary conditions which are generally applied in your vibration analysis. That is free boundary condition, fixed free boundary condition, and third one is fixed boundary condition. Okay, so these three boundary conditions will be applied in your vibration problems. So free means what? Both ends are free. If the both ends of that body is free or structure is free, then we can say that this boundary condition is free boundary condition. So for free boundary condition, this will become 0, 0. Okay. fixed and free. So for free condition this will become 0, for fixed condition there will be some value. Okay, so this will become minus EA dou u by dou x and next one is equal to 0. And for fixed both values should be there, minus EA dou u by dou x and EA dou u by this is the vibration. These are the three boundary conditions which can be applied in vibration problem. Okay, so if free condition is there, then both boundary conditions should be 0. If fixed B is there, then one term should be there. If fixed is there, then both terms should be there. Okay, so in this way you can write down your boundary conditions. Now we will see how to solve this equation which include the second derivative term, that is dou square u by dou t square. So we need to solve this equation. So we can write, so first we will write m is equal to u double dot plus k times or k matrix times u is equal to, for free boundary conditions we can write this is equal to 0. Okay, so this is for, if we suppose the boundary condition is for free case. Okay, so how to solve this equation? So as we know that in previous case we know that how to solve these algebraic equations. That is, in previous case, in previous chapters we have written our relationship like k times u is equal to f. After applying the boundary conditions we will get here 0 or some values. Okay, but the unknown should be removed by applying the boundary conditions. Okay, so if we remove the unknowns, then here will be 0 or some values, but known values should be there. Unknown values are by applying boundary conditions, these unknown values are neglected. Okay, so if we will get this type of equations, so this is the algebraic equations. So if we get the three equations, then we can solve by using the Gauss elimination method, because this is your displacement rule. Okay, so we will get by using Gauss elimination method we can solve this systems. But here in this equation, this u double dot, it is nothing but dou square u by dou t square. Okay, so how to solve such type of equations? So first we need to assume or we need to check the solution for this system. So we need to assume some solution means what? If we put the some type of solution in this equation, then the LHS should be equal to RHS. Okay, so select such type of displacement function to have LHS is equal to RHS. So if we put such type of function or such type of displacement function in above equation, then we need to get, or then we must get LHS is equal to RHS. Okay, here RHS is equal to 0. If we put our displacement function into this equation, then we must get this total term equal to 0. Then and then only this equation will be satisfied, and we can say that the solution will be used to satisfy this equation. Okay, so what is such type of equation? So we have such type of solution as, if we use the displacement function like u is equal to x times, u is equal to, one second. So if we use x times e raised to power alpha, so if we put u is equal to x times e raised to power lambda t, e raised to power lambda t. Okay, if we use, or if we put instead of u x times e raised to power lambda t, then we will get this LHS is equal to 0. So it means this displacement function is satisfying this equation. So we can use this equation to solve such problems. Okay, because to solve such problems we need some solution, and if this solution select such type of solution which will satisfy the equation. Which will satisfy the equation means what? If we put this equation into this equation, then it will be equal to 0. So this and this displacement function is satisfying this equation. So we are selecting this u is equal to x times e raised to power lambda. Okay. So if we write down this like that, u1, u2, u3, you need to write down that x1, x2, x3 e raised to power lambda. Okay. Now if we put this u is equal to x times e raised to power lambda t, then we will get. So first we know that first we need u dot. So u dot will be like a x into, because this is with respect to t, we need to take derivative with respect to t, because u dot is nothing but del u by del t. So we need to take derivative with respect to t. So if we take derivative with respect to t, this will become lambda times e raised to power lambda. Then u double dot will become, again we need to take this derivative. So this will become x times lambda square e raised to power lambda. So if we put these three values into this equation, we will get m times, instead of u double dot, it will become lambda square e raised to power lambda t into x. Okay, plus k times, instead of u we need to write down e raised to power lambda t